Hello, everyone, and welcome to task number 8. In this task, we are going to assess the performance of our trained deep neural network model and actually see if that model was effective or not. So, if you guys remember in the previous task, in task number 7, we have been able to compile and train our deep neural network model. And you guys will notice that here we only used one epoch only. But what we're going to do right now is I've already trained the model and actually let it run for many epochs, and it took a couple of hours for it to train. And now we have our frozen weights, and these are retina underscore weights dot hdf5. Okay, so what I'm going to do here is I'm going to load the weights. So I'm going to say model dot load weights, and that simply will load my pre-trained model. So you guys don't have to go and wait for a couple of hours to actually see the results with me here. But what we're going to do is I'm going to show you guys how to actually assess the performance of a classifier model. So in order to visualize the performance of a classifier model like this model, we are going to use what we call it confusion matrix. And a confusion matrix simply, it's just a visual representation of what the actual model is performing. So as you guys can see here on the rows, we put the predictions. So it might be positive class and it might be negative class. And in the columns here, we put the true class, or what we call it the ground truth. That's the actual true class. And that's like if the model was actually good, the model predictions should match what's actually true, or what's the ground truth was. So for example, if the model predicted positive, if the model said that this patient, let's say, has cancer, and in reality, the true class was actually positive, that means that's true positives. If the model predicted negative, and in reality, the true class was actually negative, then we call that true negatives. And that's when the model the model predictions matches what's actually happening in real life. However, sometimes the model actually messes up. So the model might predict positive. However, in reality, the true class might be negative, which means now I have false positives, or what we call it type 1 error. And maybe the model sometimes predicts negative. However, in reality, the true class was positive. And that's what we call it false negatives. And that's what we call it type 2 error. And in this project, we are going to print out the confusion matrix for all the 5 classes that we got. If you guys remember, we are classifying 5 classes for diabetic retinopathy, which is no diabetic retinopathy. That means the healthy eye. We have mild case, we have moderate, we have severe, and we have more of a growing kind of, like out of control type, and that's obviously the worst type, which can cause blindness in patients. So what we're going to do here is I'm going to say model.load weights, and that will simply going to load our weights here. So I'm going to go here and press Shift Enter, and that simply will load our weights. What I'm going to do next is I'm going to take that object, which is model. I'm going to use the evaluate method on that model to simply pass it along my testing data, which is, if you guys remember, I had my test generator, and I'm going to feed in batches of 32 images. And then at the end, I'm going to print out the accuracy. So if you press Shift Enter, it might take, I would say, a couple of seconds for it to run. So now I'm actually feeding in the testing data. And please note that the testing data has never been seen by the model during training. So this is just the first time the model is actually seeing these images. And you guys will notice here that the accuracy is around 84%, which is, again, pretty incredible. Like if you guys go back 10 years ago, this was like a dream to actually leverage some sort of artificial intelligence. And there is no doctor who doesn't know much. We just feed it in images, labeled images, and the neural network was able to give me 84 or 85% accuracy on images that has never been seen before. That's, again, outstanding. And to do that, with the comfort of your home, by just, doing everything virtually, it's pretty incredible. So what I'm going to do is I'm going to, as you guys can see here, just going to wait for a couple of seconds, and here we go. So now I have the testing accuracy is around 0.84, which is again really good. Next, I'm going to create what we call it labels here, dictionary, that has class 0, which indicates mild, 1 indicates moderate, 2, no DR, 3, the proliferate, and 4 is for severe. So I'm going to run that, Shift Enter. So what I'm going to do next is I'm going to create two lists. The first list has all the different predictions coming out from my model, and the next one will have our original labels. And once I create that, once I run this block of code here, you should be able to come here, generate the score, which is the testing accuracy, and to also print out all the different images, the testing images, and print out the predictions along with their original as well class. So if you guys can see here, what we're going to do is that we're going to create a for loop, and every time we are going to open our image, we are going to resize the image to 256 by 256. Generally, they are already 256 by 256, so you actually don't need to do that, but you might have, let's say, testing images, for example, that you collected maybe beyond the scope of this project, and you want it, maybe they are, let's say, a different size, let's say 512 by 512 pixels. So you actually need to go ahead and resize it before you feed it into our trained ResNet model. Next, we are going to append the image to the image list, convert them into an array format, perform normalization. If you guys remember, I had to normalize the images because when I actually trained my model, I had to normalize the images anyways. So when I actually test the model, I have to make sure that the images that I'm feeding in are also scaled as well or normalized. And then what we do in general is that we feed in the images in what we call it a 4D array, or what we call in a batch format. So that's what we're doing here. We are reshaping the image into a 4D array. And then we are going to take the model, apply the predict method to my model, pass it along whatever image that we got, that will generate predict or predictions. And please note that here we have a series of neurons in the output. I actually have 5 neurons in the output that's generating probability for each of the different class. What I wanted is I wanted to only pick the highest value in that prediction. So that's why here I'm using numpy.argmax to just give me what is the index, like which class does it belong to? Is it mild? Is it severe? Is it no DR? And so on. And here I'm going to have the predictions, and then I'm going to append that to my predictions list. And I'm going to also keep track of my originals as well. And that's essentially my original label associated with my testing data set. Long story short, I'm going to have two outputs. I have my predictions and I have my originals, and then I can compare them together and see if my model actually was accurate or it just messed up, essentially. So if you go ahead and press Shift Enter, here we go. And you guys will notice that the cell is still running, but we don't have any errors, which is great. Next, I'm going to obtain here the score, Shift Enter. And what I'm going to do next here is the following. I'm going to simply print out images, a list of images, and I'm going to print out two things on the X label. I'm going to print out the actual predictions from these images, and I'm going to print out the original as well from it. So if you press Shift Enter, you should be able to see a series of images, and you should be able to see as well, if the model was actually accurate or not. We can see that again visually, so you can actually see the image along with their predicted class, along with their original class as well. So it might take, I would say, couple of minutes for it to run. But that's from a very high level how the model is actually running. So let me pause the video and I will see you guys once the images are generated. All right, so as you guys can see here, what we are getting is amazing. So first we have our image, and here we have our prediction, which states that it's no DR, and the actual original was no DR as well, and that's great. That means the model predictions matched what's actually happening in reality in the true class. If you guys scroll down, you should be able to see again, there is no DR with no DR, no DR, no DR. We have moderate and moderate, again, pretty amazing. We have the proliferate and proliferate as well. And then no DR, and then here we have no as well DR. All of that is great. And here you should be able to see that the model actually messed up in a way. The model predicted that the actual class was actually healthy, like no DR. However, in reality, the original class was actually moderate. So that means there is a model mess up here. And maybe we need to add additional training data set. Maybe we need to perform some sort of augmentation. Maybe change the model architecture, for example, and try to improve the generalization capability of the model, and so on. So many ways of improving the model. But that's from a very high level how we actually assess the performance of the trained model, which is again pretty powerful. So you will find that actually the model messed up sometimes as well. So there is a lot of, so for example, here there is no DR as well. Here we have, let's say, severe. The model predicted severe. However, in reality, it was moderate. And what we could do here is we can actually print out the classification report for us and print out the confusion matrix. That will give us kind of a summary of all the different classes and actually how the model is actually performing in real life. And that will be our mini challenge number 6. So please go ahead, pause the video, and I will see you guys after the challenge. All right, hope you guys were able to figure out the challenge. What you guys can see here, I actually have the solution here. You can go ahead and print out the classification report as follows. If you actually press Shift Enter, if you press Shift Enter here, you should be able to see the confusion matrix, and you should be able to see here the actual classification report. So as you guys can see, I have around 84% accuracy in total. And here I have a summary of all the precision and recall. So you will find that the actual model is doing great on the no DR class, which is around 97. However, it's actually performing quite poorly on the severe case and the proliferate. And that's actually might be because we don't have a balanced data set. And that's one of the key problems that we have in this data set, that if you guys go up, if you guys remember, when we printed out our percentage of distribution of our data set, we find that the no DR was actually almost half of the data set, which is a healthy case. And we have the severe is almost like 6% or 5% here, and the proliferate is around 8%. So these are, I would say, the underrepresented samples in the data set. So because we have an unbalanced data set, it's really hard to push the accuracy to, let's say, 95%, for example, which means that I need to go ahead and collect additional more data to be able to push that performance a little bit further. And if you wanted to check out here our confusion matrix, you should be able to see all the different classes, all the different samples that have been correctly classified, and here all the different samples that have been misclassified. So we actually correctly classified a lot of samples and misclassified 15 samples here, 2 there, 4, 21, and so on. And as I mentioned, we can push that forward by adding additional data set. And that's it. That's all I have for this entire project. I hope you guys enjoyed it. Let's go ahead and recap what we have done so far. So in this project, we have been able to develop a deep neural network model to detect and classify our diabetic retinopathy. And we covered, or we understood, the problem statement and business case. We imported our libraries and data set in task number 2. And then in task number 3, we performed data exploration and data visualization. And then in task number 4, we performed data augmentation and we created data generator. And then in task number 5, we understood the theory and intuition behind convolutional neural networks and residual neural networks. And then in task number 6, we built ResBlock-based deep neural network model. And afterwards, in the next task, we compiled and trained our model. And then finally, in task number 8, we assessed the performance of the trained model. And that simply concludes our project. I hope you guys enjoyed it and see you in future projects.